then we should begin. And as I always begin, there's always two pieces of advice. I know if you've been with me before, you've seen them, but we say them because they're important. Do problems. That's why we're here. Take care of your health, because this is just one exam. You know, this is not, in the grand scheme of things, it won't make that much of a difference. And I know it feels like that's not true, but when I was an undergraduate, I remembered I saw a cartoon in the newspaper, our student newspaper. And it was a drawing, and on the left, your life if you ace this exam. Nice house, cool car, you're laying in a hammock, life is good. Then on the right, your life if you don't ace this exam. Nice house, cool car, you're laying in a hammock. Because ultimately, you'll be fine. You'll be fine. And so remember, this is just a passing thing. You'll be fine. Eat good food, get out, enjoy the weather, scream in your pillow as needed, but take care of your health. So, since people are excited about word problems, we start with the wordiest of word problems. Tanks and tank mixing. Bring in the brine. All right. So this is a great thing that systems are really well built for, because you have two things which are interacting, and ultimately that's what systems, which is what this exam is about, it's built for this. It's like, okay, how do we understand how things interact? So, we have a lot of words here, but we see there are two tanks. Okay, well that's good. Let's start building a picture, because I think pictures help a lot. Okay, so we have two tanks. So we'll just draw tank 1 and tank 2. Okay, so here we go. And we're going to just keep track of what happens as we go through here. So tank 1 has 10 gallons of brine. Brine is just a fancy way of saying salt water. There is 1 gallon per minute with a concentration of 8 ounces of salt per gallon of brine being pumped into tank 1. So that's our input. Okay, so we were told it's 1 gallon per minute, but then it's interesting, they didn't give us a number here. It's A ounces per gallon of salt. Okay, there are 2 gallons per minute being pumped out of tank 1 and out of the system. So in other words, it's completely gone. So that's 2 gallons per minute. Okay. And there are 4 gallons per minute being pumped from tank 1 into tank 2. Okay, so we have something going from tank 1 into tank 2 at 4 gallons per minute. All right, so that's the first bullet point. So far, so good? All right. Tank 2. 25 gallons of brine, all right, 25 gallons. There are 6 gallons per minute with a concentration of B ounces of salt per gallon of brine being pumped into tank 2. Okay, so again, we have things coming in. We know it's coming in at 6 gallons per minute. And there are B ounces per gallon. All right, yet another thing we don't know. There are 5 gallons per minute being pumped out of tank 2. Okay, so 5 gallons per minute comes out. And there are 5 gallons per minute being pumped from tank 2 into tank 1. Okay, so we have 5 gallons per minute going that way. All right, so there's our setup. And we can sort of look and say, okay, does this make sense? Well, one of the things is we can say, let's look at the in and out. How much is going into tank 1? How many gallons per minute comes into tank 1? 6. How many goes out? 6, that's nice. Tank 2, how much comes in?
6.
Well, we have 10, right? 4 plus 6, 10.
And also 10.
Oh, you anticipated, yes. How much leaves? 10. Good. All right, so that's good. So in other words, nothing's changing with the levels. It's staying where it is. So it stays at 10 and 25. That's good. I like that. Then we have this last part. Given that in the long run, so long run says t goes to infinity, the amount of salt in the tanks will approach 25 ounces of salt in tank 1, 55 ounces of salt in tank 2. What is A and B?
Well, it seems pretty linear to me.
It does, but is it?
Yes.
Oh. Well, it depends what you mean by linear. So we'll find out, and time will tell. Okay. So how do we start going through this process? Well, let's make some variables. What do you want to call the amount of salt in tank 1? Yeah, X is great. X, amount of salt in tank 1. And really we think of this as X of t. It'll change with time. Okay, how about, what do you want to call the amount of salt in tank 2?
We'll call that Z.
Yeah, we'll call it Y. Sounds good. I anticipated. So the amount of salt in tank 2. All right. We have X and Y. Now, you might say, do I need to worry about the initial conditions? And we'll get to that in a second. Okay, let's start with what we know. Well, let's talk about change. Changing X prime. Okay, so X prime. What does X prime mean? What's the meaning of X prime? How X is changing, right? Prime is derivative. Derivatives are change. So we're asking for how is X changing? Now, when you're doing tank problems, here's the thing to remember. The change is equal to in minus out. The only way you can change is either something came in or something went out. So, let's talk about what's coming in. Okay, so the ins, there's two things coming in. Let's start here. So this 5 gallon per minute is from tank 2. How much salt is going to be inside of that? Well, we can think of it as we have, what is it? We could say flow rate times concentration. Yes? Is that a formula we learned at some point? Okay. So what's the flow rate here? So 5. What's the concentration of this fluid? Well, it's coming from tank 2. It's Y over 25. So Y is not the concentration. Y is just how much salt there is.
Also known as just Y over 5.
Well, when you combine, yes, that's true. But we'll start here. So 5 is the flow rate. Y over 25 is concentration. Okay. So far, so good? Yes? Yes? Cool. All right. We also have another in. How much salt is coming from the outside? Oh, yeah, eh? You betcha, eh? Because 1 gallon per minute, 8 ounces per gallon. Okay. Subtract. Okay. Now, what's leaving? Well, we have two things leaving, but it doesn't matter where it leaves. It's still the same thing is happening. So we'll just think of it as just there's one big output. So combine, what's the flow out? 6. What's the concentration? X over 10. Okay, so that's X prime. Let's do the same thing with Y prime. And I know you're skeptical I'm going to run out of space. I am too. But that's okay. We'll almost make it. Y prime. Okay, so let's start with the ins. This, coming from tank 1, what do we have? 4 times X divided by 10. Coming from the outside, what do we have? 6b. Okay, then leaving, what do we have? minus 10 times y over 25. Okay. Now, what do we know?
We know that we can simplify this.
We can, but hold on. We'll get there. What do we know? Well, let's come down to this statement. In the long run, the amount of salt in tank 1 goes to 25 ounces. What does that say about X? X goes to what? X goes to 25. What happens to Y?
Y goes to 55.
Y goes to 55, because there's 55 ounces, yes? I'm not saying that X is always 25, I'm saying X goes to 25. So far, so good? Now the tricky part. What happens to X prime and Y prime? And why does that do that? This is sort of the conceptual leap.
Do they go to 0?
0, why that?
Well, because as t approaches infinity, x will go to 25, therefore it will stay at 25. It will get closer to being at 25 the closer it is to infinity, therefore x prime will get closer and closer to 0.
So yeah, that's the right intuition. So as we're getting closer to 25, we're not changing much. How do you say you don't change very much? Well, your derivative is small. And the closer we are to infinity, the less we change. So the derivatives go to 0. So now what can we do with this information? Yeah, we can take this information here and we can plug it in. All right, let's see what that gives us. We get 0 is equal, now 5 over 25 is 1/5. Y, 55. Then plus A, 6 over 10 is 3/5. And then X is 25. So here, as t goes to infinity. Well, 1/5 times 55?
Is
11. 3/5 times 25? 15. 11 subtract 15?
-4.
Negative 4. All right, so 0 is equal to a minus 4. We'll come back and try to solve that. I think we can. Y prime.
Yeah, that's difficult, isn't it?
It can be for some people. 4/10 is 2/5. X, 25. 6b, we don't know it, but we'll know it soon. 10 over 25?
2/5.
2/5. And then Y, 55. Say, that's 6b. 2/5 times 25 is 10. 2/5 times 55?
22.
22? Sure. Maybe.
55 divided by 5 is 11 times 2 is 22.
Okay, all right, okay. All right.
What are you guys laughing at?
So 6b, let's see. So 6b minus, all right, I lost my concentration. Sorry, what? So 4/10, okay, all right, 2/5 times 25, 10 minus 22, so that's 6b minus 2? Is that right? Sorry, I got distracted. Okay. So, oh, is it 12? Sorry. There we go. That's what happens when you get distracted. 6b minus 12, yes. Yes, thank you. 10 minus 22 is in fact minus 12. Okay, so what is A? A is 4. Oh, it was easy to solve. What is B?
2.
B is 2. And there we go. All right, see? Not so bad. Word problems aren't scary at all. All right. One problem down. Any questions? Use a picture. Remember, in minus out. Flow rate times concentration. This will feel familiar. All right. Number 2. Using the following system of differential equations, find a differential equation satisfied by y. In other words, a differential equation for y with no terms involving x. So this problem falls under what we would call elimination. Our goal is to eliminate, in our case, there's no terms involving x. We want to eliminate the x. We only want y. So instead of many equations, we want a single equation. All right, well, how do we do it? Well, the key here is we're going to use D notation. Now, D stands for derivative. It's like Cookie Monster. D is for derivative. That's what it means to me. D is for derivative. That's what it means to me. D is for derivative. That's what it means to me. Derivative, derivative, derivative starts with D. I think that's how it goes. It's been a while. All right. So, well, what do we do? The goal is we want to rewrite this using our notation. So x double prime becomes d squared. And then x is 1. So x double prime plus x is d squared plus 1 times x. Y prime, what would that be? D times y, right? And so this becomes d minus 1 times y equals e to the minus 2t. So we're rewriting the equations using our D notation, then we're factoring out our x, and we're factoring out our y. All right. X prime plus 4x. That's something times x. What goes in the box? D plus 4. All right. Y prime plus something y. What goes here? D plus 1. And the 2 cosine t stays as 2 cosine t. Now, we'll rewrite this as a matrix. We say, all right, well, what do we have? We grab our coefficients, d squared plus 1, d minus 1, d plus 4, d plus 1, times xy equals e to the minus 2t, 2 cosine t. All right. Now at this stage, we're ready to use what I like to call Cramer's rule. It's not quite the same as Cramer's rule. There's a small twist, but you should think of it as Cramer's rule and say, all right, let's use our Cramer's rule. Now what does that say? Well, we have to remember what we're looking for. We're looking for y, so we're going to take the determinant of the coefficients, d squared plus 1, d minus 1, d plus 4, d plus 1. The nice thing is, this you should just treat like you would algebra. So you can multiply expressions involving d, you can add expressions involving d. Life is good. Times y equals a determinant on the other side. Now, you have to make sure you replace the right column, because you're going to use the functions replaces one of these columns. Which column do you replace? The first or the second? The second column. Now why? Well, because it's y, right? The first column, that's your x column. It's attached to the x. The second column is your y column. It's attached to the y. So you replace the column that you're working to find. So I'm going to keep the first column as is. D squared plus 1, d plus 4. Then we have e to the minus 2t and 2 cosine t. Okay. Well, a determinant, our first one of the night. Great. So we go down our diagonal and go subtract up the other diagonal. So we're going to have d squared plus 1 times d plus 1, subtract d plus 4 times d minus 1, all of this times y equals, and then over here, similar, d squared plus 1 times 2 cosine t, subtract d plus 4 e to the minus 2t. All right. Well, the good news is we're a good chunk of the way there. Then we start doing our expansion. We have d squared times d makes d cubed. Then we have a d squared plus d plus 1. And then we'll subtract d squared minus d plus 4d minus 4. Okay, all that's times y. Let's see, we have d cubed. D squared subtract d squared. Ooh, nice. 0. Cancels. Aha. Okay, good. Then let's see what we have. Well, inside we have minus d plus 4d. That's 3d. But remember we're subtracting that. So d subtract 3d is minus 2d. 1 subtract minus 4 is 1 plus 4 is plus 5. Remember to use parentheses. Parentheses are friends. A lot of people lose points because they forget to use parentheses properly. We don't want to do that. That would just feel silly. Okay, so that's good. We made great progress on the left-hand side. So we should start chipping away on that right-hand side. All right, so let's think about what happens. If I take d squared times 2 cosine t, that means take 2 derivatives. What happens when you take 2 derivatives of cosine t? What do you get? Negative cosine t. So it's minus 2 cosine t plus 2 cosine t, right? Because the first term is, this is your d squared 2 cosine t. And then this is simply your 2 cosine t. Now, similar, what's the derivative of e to the minus 2t? Yeah, the negative 2 comes down. So we'll have negative 2 comes down. There's a minus here, so that makes a plus 2 e to the minus 2t. This right here is minus d e to the minus 2t. And then we'll have minus 4 e to the minus 2t. Okay? Well, things simplify. And what do we end up with? Well, you'll notice the cosines cancel. Oh, how about that? D cubed y, what's another name for that? Y triple prime. D times y, y prime. 5 times y is 5 times y. The cosines cancel. 2 e to the minus 2t. Subtract 4 e to the minus 2t. Leaves us with a minus 2 e to the minus 2t. And what comes next? Yes, we're done. Done. I will say, historically, students have liked problems like this. We'll see if the trend continues. Any questions? Yes. So where did this negative 2 cosine t come from? Well, so it came from distributing here, right? So I'm taking the 2 cosine t times d squared. So d stands for derivative. Okay, so d squared stands for 2 derivatives. So start with cosine. Derivative 1 of cosine is negative sine. And then take the derivative of that is negative cosine. So that's where you get that from. Any other questions?
Would the question wording just change to solve if you wanted to solve?
Yes, so that's a good point. Notice the key word here is the word find. Make sure you follow instructions. Do it what it asks. Don't keep going. You know, once you're like, I got to the point where I found what the problem asked me to find, stop. Anything you do after that won't get you more points, but it will cost you time. And we don't want you to lose your time. Your time is useful for double checking your work. Anything else? All right, good. Well, moving right along. Number 3. So consider the system t cubed x prime equals 2t squared, t to the 4th, negative 2, 3t squared x. So this is linear. It's just that this time, this matrix here depends on t. And it can. There's nothing that says it can't. We have no tools, but still, that doesn't mean it can't. So you won't see that very often. So there's 3 things it's asking us to do. Part A, verify that these 2 functions are solutions. All right, there's a key word here for part A, which is verify. So how does one go about doing a verify problem? Yeah, you plug it in. You don't have to be creative. You just plug it in. Now the nice thing about verify problems, if you see a verify problem, you're like, free points. Because I know what's going to happen. I plug it in, and I'm going to get things that match. Now if they don't match, what do? Repeat the work until you find your mistake. So you just keep going until you've got your points. So this is we love this, free points. Woohoo! Okay, so let's start with our x1. When we say plug it in, we mean plug it into both sides. So on the left-hand side, well, we're going to have t cubed. Make sure you get things. And then it says take the derivative. So when you take a derivative, you take the derivative of each entry. Derivative of t to the 4th, 4t cubed. Derivative of 2t squared, 4t. And we go ahead and multiply these, and we'll get 4t to the 6th and 4t to the 4th. All right, that's the left-hand side. We haven't finished verifying. We're halfway. We do the right-hand side. So on the right-hand side, well, we take our 2t squared, t to the 4th, minus 2, 3t squared. We're just copying. By the way, there's going to be a lot of copying that happens on exams, for this exam in particular. It's just be patient, and it doesn't hurt to double check that you've copied things correctly. And then this is a problem which has a built-in check. If the answer is wrong, you're like, well, whoop, made a mistake. Go find it. Let's see, what do we have? We'll have 2t to the 6th plus 2t to the 6th. So we're doing our matrix multiplication. So row in the first one, column in the second one. So then we have minus 2t to the 4th and plus 6t to the 4th. And we add, we get 4t to the 6th in the top entry, 4t to the 4th in the bottom entry. What did you look at that? That's right. What do we see? We see, aha, this is a match. That's the thing we need. That's the verification, that the left-hand side equals right-hand side. Okay, well that was a good warm-up. Let's do it again, because we have x2. So it's going to feel very deja vu-y, but you do the work, you get the points, you don't take the final. Life is good. All right, t cubed, starting with the left-hand side. What's the derivative of t cubed? 3t squared. Derivative of t? 1. So the left-hand side says we should have 3t to the 5th and t cubed. What is that right-hand side saying we should have? Well, okay, again, we copy down that matrix. And we write down what our x2 is, namely t cubed t. All right, 2t squared times t cubed, 2t to the 5th, t to the 4th times t, t to the 5th, minus 2 times t cubed, minus 2t cubed, 3t squared times t, plus 3t cubed. We put it together, 3t to the 5th and t cubed. Okay, and do they match? Yeah. Nice. Now, you don't actually have to say that out loud during the exam, but mentally you can say that, like, your internal dialogue. Okay, so we're done with part A. All right, so on to part B. Find a solution to the system where when we plug in 1, we get the value negative 1, 1. Now, let's see, is it the first solution? No, that would give us 1, 2. How about the second solution? No, that would be 1, 1. How are we supposed to find more solutions? It would be super if we had a way. That would put us in a good position to solve the problem. That's how super it would be. A suggestion.
Yeah. What about negative t cubed over t?
Well, negative t cubed upstairs and t downstairs won't work. It's not a solution to the original system. Now, you could negate both top and bottom, but then you'd have negative 1, negative 1. Superposition. Aha! Someone is able to crack my secret code I've been working on years to hone. Okay, so this is used a lot. Sometimes we use it so much we don't even draw attention to it anymore. But superposition, that's an important idea. Now, what does that say? Well, it says if you have something linear, which this is, it's a linear system. Then if you have, and it's homogeneous, I should add that. And it is, it's homogeneous. Then if you have some solutions, you can make many. And so for part B, we say, okay, we can make a lot of solutions by taking some constant times the first solution, plus some other constant times the second solution. And for arbitrary choice of C and D, that's a solution. Now, we say, okay, cool. So our goal is to say, but what's the right choice for C and D? So how do we figure out the right choice? Plug it in. And which point do we plug in? 1. Yeah. Make sure you pay attention. Sometimes things are slightly different, so we want to make sure we grab that. Okay, so we know that when we plug in 1, we want negative 1, 1. Well, that should be C. The nice thing about 1, it's really easy to plug in. So it would be C times the vector 1, 2, plus D times the vector 1, 1, which is C plus D, and 2C plus D. Another way to say this is that we have really 2 equations. That is, C plus D is equal to negative 1, and that's the top entries. 2C plus D is equal to positive 1. That's the bottom entries. 2 equations, 2 unknowns. You're going to see it. Probably a couple times. So make sure you know how to do it. Don't get me into trouble when you get into your engineering classes and be like, 2 equations, 2 unknowns. I've never met them. So, all right. So how does one solve such a thing? Oh, elimination, yeah. You can do substitution, but I would say learn elimination. I'll subtract the bottom from the top. C subtract 2C is negative C. D subtract D is 0. I saw that D's had the same coefficients. That's why I just did a straightforward subtraction. Negative 1 subtract 1 is negative 2. What does that tell us about C? C is 2. So we have that 2 plus D is negative 1. What does that tell us about D? Negative 3. So we say, okay, now we plug that in. So that tells us that for part B, the answer we're looking for is 2 times the first function, t to the fourth 2t squared, minus 3 t cubed t. We can even smash it together. 2t to the fourth, subtract 3t cubed, and then downstairs, 4t squared, subtract 3t. So there's our answer. You don't have to put them together, unless it somehow says put them together. There are times when you have to do things, but usually we'll point something out on the next problem, I think. Okay, good. Are we good with part B? Nice. All right, which brings us to part C. So given that we know x of 1 is negative 1, 1, can we determine x of negative 1? No. If yes, give the value. If no, briefly explain why not. Now, someone seems to have indicated perhaps it's a no. Now, before we get to why it might be no, let's think about why we might be tempted to say yes. This is why we're tempted to say yes. It's like, look, I have a function. This is a nice function. Nothing crazy is happening with it. You plug in -1, and life is good. So why are you saying it might be a no? Why do you have to rain on our parade?
I wasn't thinking. I apologize.
No, you're right. The answer is no.
I don't have a reason.
Okay, all right. It is no. Can anybody perhaps think of a reason why the answer might be no? Sorry, what? Oh, time can be negative, sure. You know, you go backwards in times. Oh, there's two people sitting next to each other. Wait, now they're pointing to each other. No, rock, paper, scissors. Oh, there we go.
Because you don't know what x or -1 should be in like a matrix.
Well, it's not that. That's not the problem. I mean, because if they had asked us, can we determine x of 2, the answer is absolutely. X of 2 is totally cool. That's the bee's knees.
Is it perhaps that x of -1 loses uniqueness and therefore they're not independent?
Well, but what's happening? Oh, good thing this one wasn't on the test. But what's on the test? Who knows? Okay, so do you want me to tell you, or should we play a little game? All right. What is it we need here? What? No, we don't need an E. An A is an excellent choice. Oh, wow, that's pretty good. You only needed one letter. Whoops, Wronskian. Good. See? You just needed one letter. Okay, so here's the thing. There's the question of uniqueness. So to say that we can determine x of -1 says, yeah, there's a unique function that gets us to -1. How can we test if uniqueness exists? The Wronskian test does. So we take the Wronskian of x1 and x2. So know how to do that. So the Wronskian is a determinant. What goes in the first column? The functions, the first function. So t to the 4th, 2t squared. What goes in the second column? Second function, t cubed, t. Now we take the determinant, t to the 4th times t is t to the 5th. 2t squared times t cubed is minus 2t to the 5th, which ends up with negative t to the 5th. Now, does the Wronskian ever have a problem? Does it ever zero anywhere? Yeah. This vanishes. In other words, it's equal to 0 at t equals 0, which means you're fine as long as you stay away from 0. But as soon as you get to 0, all bets are off when it comes to uniqueness. So you can't say anything about what's happening below 0. Now, I know that you're saying, but wait, there's a solution. Yes, it's a solution, but there's lots of choices that you could have. See, when you hit 0, it's a choose your own adventure for what goes on below 0.
How would you know if it's above t or below t where it's undefined?
Well, the point here is that the Wronskian, as long as the Wronskian is non-zero, you're good to go. You've got uniqueness. That's the punchline of the Wronskian. And so we know we started at 1. So we say, okay, we know where we're starting. We're starting at 1. So as long as I stay away from 0, life is good. The problem is, to go from 1 to -1, it's hard to avoid 0. You kind of have to pass by. You know, there's no like Super Mario pipe that you jump in and like womp, 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 and then you show up on the other side. I'm looking forward to playing Super Mario Wonder this week, you know. I downloaded it last night. So, all right. So anyways, that's a little subtlety. Mostly I wanted to ask this one just to make sure, hey, don't forget about that Wronskian. It's good stuff.
So could we still say from 0 to infinity?
Yeah, from 0 to infinity, it's this. Below 0, who knows? Who knows? All right. Now, the good news is, I think for the rest of the problems, we're basically all eigenvalues all the time. So here we go. Number 4. Find the general form of solutions for x prime equals 2x minus y and y prime equals 3y minus 2x. All right. So I want us to start practicing eigenvalue techniques. So first thing is, we're going to say, let's turn this into a matrix, because in order for us to do eigenvalue techniques, we have to have a matrix. So we're going to rewrite this system in a nice matrixy way, which is to say, since we already use x and y, I'll go to a letter z. Z prime equals our matrix z, where z here, just to emphasize, this is xy. All right, so what goes into this matrix?
2, -1, -2, 3.
It's the coefficients, right? Okay, so I can do something like, I can write down 2, -1, and 3, -2, and hold on. Why not?
Well, because 3 is a coefficient for the y variable. You can't put it in the first column.
Oh my gosh. Whoa. Someone was trying to trick us. Y prime should have been -2x plus 3y. Ooh, good catch, good catch. Now you might be wondering, have they ever done that on an exam? Yes. Did Steve write that problem? Yes. Did he catch about a quarter of the students who made that mistake? Yes. So pay attention. We know people are quick. Oh, did I copy it down wrong again? I know, there was a typo, I fixed it. Just to have fun. You can still solve that one. But I just wanted to have fun and point out, pay attention. Pay attention. Because we know people like to go fast. They pride themselves like, I'm going to finish this 75-minute test in only 52 minutes. You don't get extra credit for finishing fast. The only points you get are being right. So go ahead. Make sure they didn't try to do something subtle on you. All right. So now, the first thing that we do whenever we see our matrix problem, we always do eigenvalues. So you want to just no matter what, eigenvalues are coming. So you got to just have that eigenvalue procedure down cold. So you're going to take a determinant of, in this case, 2 minus lambda minus 1 minus 2, 3 minus lambda. So this is our a minus lambda I. And so we start working through that. So this is 2 minus lambda times 3 minus lambda. Subtract minus 1 times minus 2. Expand, you get 2 times 3 is 6. Minus 2 lambda minus 3 lambda plus lambda squared minus 2. Lambda squared minus 5 lambda plus 4. And remember, the goal is to set this equal to 0. So we're after the roots. Well, if life is good, we've lived a good, clean algebra life, what should happen? It should factor. So, whoops, that's still 0. So lambda minus 1, lambda minus 4. If you're not sure, just repeat it, right? Lambda squared minus 4 lambda minus lambda is minus 5 lambda and plus 4. You can always use quadratic formula. That's perfectly fine. So we now have our eigenvalues 1 and 4. All right, now after your eigenvalues, what comes next? Eigenvectors. Now, you won't always find eigenvectors. There are ways to avoid that. However, this is a case where we have to. Okay, so what do? Well, we start and we take, when we have distinct real roots, we've got to do them both. So, well, all right, lambda equals 1. If we use lambda equals 1, we're going to take our a minus lambda I, we're going to put in 1. So let's see, 2 minus 1 is 1, minus 1, minus 2, 2. We want to multiply that by something and get 0, 0. The something is what we're calling the eigenvector. What's a vector that works here? Sorry, what? 1, 1. Yes.
Is that shortcut just taking the transpose of one of the rows?
So the shortcut is not easy to see on this example, so maybe we'll do an example where it's a little easier to see, and then we'll talk about it. At this stage here?
No, I'm finding the eigenvalues.
For this stage here?
Should you always write the a minus lambda I?
Underneath it? You don't have to. I just write it, just to emphasize. Now, if you're a rebel, you can write lambda I minus a. Now, there are people in the math department who would come in at this point and say, Steve, I am ashamed of you. You should never write a minus lambda I. It should always be lambda I minus a. And then I say, I record the videos. You don't. I get to say what it is. No, I would never say that to that person. So, no, I just do that because I'm a forgetful person. So, all right, lambda equals 4. Okay, here we go. Lambda equals 4. So I'm putting in lambda equals 4. So 2 minus 4 is negative 2, negative 1, negative 2, negative 1. Okay. So someone is saying, well, how does this shortcut work? So let's just remind ourselves of the shortcut. We pick a row. It doesn't matter. I'll pick this second row. In this case, it really doesn't matter. And the way you do this is you say, okay, I'm going to take this and write it backwards. So negative 2, negative 1. And then I'm going to flip a sign. Doesn't matter which sign you flip. I'll make the first one positive. And there's the eigenvector. If, when in doubt, just multiply. You get minus 2 plus 2 is 0. Minus 2 plus 2 is 0. You can always sort of undo and say, let me check. It's okay to check yourself. As the great mathematicians would say, you should check yourself before you wreck yourself. So, all right. So we've got our eigenvalues. We've got our eigenvectors. So now what we can do is we can find a general form for Z. And I don't know why I'm going in this strange right to left pattern. Oh well, it doesn't matter, it's okay. So what we have is eigenvalues, eigenvectors become solutions. We have two solutions. So our first solution, well, would be e to the eigenvalue, t, so let's do lambda equals 1, so it would be 1 times t, or simply t, times that eigenvector, x2, e to the eigenvalue, t, so e to the 4t, times eigenvector. And so then superposition, some constant, e to the t, 1, 1, plus some other constant, e to the 4t, 1 minus 2. Is this our answer? And obviously I typed X when I should have typed Z. Now is this our answer? Yes. And why not? So, two questions. Is this our answer? No. Why not? We worked hard. We should get points. And you would get many points here, but you would not get all the points. And our goal is to get all the points. Yeah, we started here. The matrix and vector stuff we introduced. That's not the problem. So now what we have to do is we have to disencode. That doesn't sound like a word. Decode? Sure, we can make that a word. We have to somehow get back. So what we can do is we can say, well, look, let's just put it all together. This becomes c e to the t plus d e to the 4t in the top, and c e to the t minus 2d e to the 4t on the bottom. And remember that z, the top is x, the bottom is y. So we say, okay, so in that case, x is some constant e to the t plus some other constant e to the 4t, y, some constant e to the t minus 2, that constant d e to the 4t.
Now we're done.
And yes, we are done. We'll put a box. Life is good. All right. Any questions?
Why, I guess, can you just uphold that z to x, y in that vector form? Or would that not be correct?
We still wouldn't want that because that's still something that has been introduced. In the vector, that's something not inherent in the original problem. So you really, if you start with things without matrices and vectors, you should end without matrices and vectors. And by the way, you don't actually have to do the eigenvalue technique. I mean, you can do things such as elimination and substitution, but the eigenvalue techniques actually makes things generally a little bit faster once you get the hang of it. Any other questions?
I guess if you switched around the equation with the bottom to the x down below the y prime, it's still work out the same way as the t.
Oh, yes. In fact, one of your eigenvalues would still be 1 if you worked it out that way. I don't know, did you try it? One of your eigenvalues would still be 1, and the eigenvector would still be 1, 1. You can try it out. Try it. Do this at home. No. You can do it here too. Okay, number 5, our halfway point. Solve x prime equals 2, 4, minus 1, 6x with some initial conditions. X of 0 equals 3, 2. Now, at this point, we have no idea what kind of eigenvalues we're dealing with, and depending upon what eigenvalues we have, we'll do something different. So, time for us to first figure out what's going on here. What are these eigenvalues? And, so we'll find out. So, same procedure as before. Since we've talked a little bit about it, I won't say quite as much as we did last time. So we set up our determinant of a minus lambda I. So we'll get 2 minus lambda times 6 minus lambda. Subtract negative 1 times 4, which would be 12. Minus 2 lambda minus 6 lambda plus lambda squared plus 4, which would make this a lambda squared minus 8 lambda plus 16. We say, ooh, does this factor in a nice way? Yes. Can anyone tell me? Lambda minus 4, lambda minus 4. All right, repeated eigenvalues. Good. So repeated eigenvalues, this is our happy state. This is the best case scenario for us. All right. Now, there's actually 2 ways to do this. I can show you both ways. The other way, you will not have as big a smile. But let's do it, first off, our happy way. What makes us happy when we see repeated eigenvalues? What's great about the repeated eigenvalue case? We have what? We have an equation for it. Yes! Now, when you say we have an equation for it, we have an equation for e to the at. It is, I probably should have written down what the eigenvalues are, 4 and 4. E to the lambda t times the identity plus a minus lambda I times t. That's the equation we have. That's on our equation sheet. Now you might say, okay, how does that get us closer to our answer? Well, first off, let's actually follow it through. So, e to the lambda t, well, lambda is 4, so that's e to the 4t. The identity looks like 1, 0, 0, 1. A minus lambda I, so that's going to subtract 4 on the diagonals. So that would be 2 minus 4 is negative 2, 4, negative 1, positive 2 times t. So that's e to the 4t, 1 minus 2t 4t minus t, 1 plus 2t. Now, this is not our answer. But we're close. We found e to the at. E to the at isn't just any matrix. It's like fundamental to solving problems. So why is e to the at so cool? So cool thing about e to the at. Well, there's probably not just one thing. So a cool thing about e to the at. Well, that is to say x prime equals ax. Initial condition x of 0. So if you have an initial condition value problem, then the solution is equal to e to the at times x0. So if you can compute e to the at quickly, it's a win. We have e to the at quickly. Repeated eigenvalues means we get that done quickly. So, do we know what x0 is? Yeah, it was given to us. 3, 2. So, that tells us that our answer is going to be e to the 4t times the 1 minus 2t, 4t minus t, 1 plus 2t, times 3, 2. So, well, okay, we should simplify this. So we're going to get 3 times 1 minus 2t, plus 2 times 4t, 3 times minus t, plus 2 times 1 plus 2t. And let's see, what does that become? We'll have 3, then we'll subtract 6t, add 8t, that's plus 2t. Down here we'll get a 2. Then we'll subtract 3t, add 4t, which is a plus t. Yes? No? And at this point, we
Plug in.
are done. That's the answer. Yes? No? Does it seem like we stopped too soon? It's like, come on, Steve, make us do more work. All right, good, I can do that. Should I show you the alternative method? Just so you can say, I can appreciate my options. All right, alternative method. So the alternative method kicks in when you say, okay, I have repeated eigenvalues. And I forgot that I have a formula sheet. Well, if you were looking for the general form, yes. So if you're looking for general form, which is not what this problem asked, but that's a good question. So if you're looking for general form, the thing is, e to the at, the columns are solutions. And that's because it's a fundamental matrix. That's true of any fundamental matrix. It just happens e to the at is a really cool fundamental matrix. So you could say that the general form would be e to the 4t, so well, some constant c, e to the 4t, times the first column, so 1 minus 2t minus t, plus some constant d, e to the 4t times the second column, 4t, 1 plus 2t. Now, it should be noted, general forms are not unique, as we are about to see. Okay, so if we weren't smart and forgot we had a formula sheet. But I think that I'm willing to wager most of you are people who believe in the formula sheet. So, but suppose we forgot. So what you would do next is when you have repeated eigenvalues, you have to say that in the 2 by 2 case, that tells us we're going to have a missing eigenvector. So it got lost along the way. You know, it hung out with the wrong crowd, and it's a sad story. But okay, so we have a missing eigenvector. So what we do is we're going to find two things. We're going to find, find two vectors, v and w, where a minus lambda I times v is 0, and where a minus lambda I times w is v. So this is the procedure you have to do if you forget about e to the at. Why do we want these? Well, the reason we want these is our first solution is going to be e to the eigenvalue t times eigenvector, because this v is really an eigenvector. The second solution is e to the eigenvalue t, and this is like, well, we're channeling our inner, we want to bump. And we say, well, okay, cool, we bump, we multiply by a v, but it doesn't quite work. We have to add a little fixing term, that's the w. So that's the second solution. Okay, so we have to find these vectors. Notice we didn't actually find any eigenvectors here. We didn't find a single eigenvector. That's okay, we'll find it now. All right, so here we go. We have a minus lambda I. Lambda is 4. A minus lambda I is going to be minus 2, 4, minus 1, 2. Okay. And I should switch colors, you know. I have a condition in where I have to switch colors every few minutes, otherwise I lose track of my work. Okay. So, we'll start with our v. Minus 2, minus 1, 4, 2. Is there a nice vector for v? Two, 1. Okay. Now we found our v. So v goes in over there. Is there a nice vector that we can pick? Negative 1, 0. Great choice right out the bat. And you can verify, look, 2 plus 0 is 2. 1 plus 0 is 1. Ha-ha, ho-ho-ho, ho-ho, ho-ho. Okay. So, we have our solutions. E to the 4t times 2, 1. Here is e to the 4t, t times 2, 1, plus minus 1, 0. Or if you like, that's e to the 4t, 2t subtract 1, t. Now, once you have your x1 and x2, at this point you're like, yes, I'm definitely going to use the formula sheet. But we might as well just embrace it. All the way to the end. We have that superposition. Our solution looks like some constant c, e to the 4t times 2, 1, plus some constant d, e to the 4t, 2t minus 1t. I pulled the page back so I can remember that my initial condition I want to satisfy is 3, 2. So we want x of 0 to be 3, 2. So that's some constant c times 2, 1 plus some constant d times minus 1, 0. If we combine 2c minus d on the top and c, this leads us to a system of two equations. 3 equals 2c minus d and 2 equals c. Well, one of them is easy. Yes, I agree. C is 2. Well, that says 3 is equal to, C is 2. 2 times C, that's, I got ahead of myself, is 4 minus D. So what is D? So D is 1. So our answer is 2 e to the 4t, 2, 1, because C is 2, plus 1 e to the 4t, 2t minus 1 t. Well, we can combine. That's e to the 4t. 2 times 2 is 4, plus 2t minus 1. Then we have 2, and then we have plus t. So this becomes e to the 4t, 3 plus 2t, 2 plus t. Okay, were we close? Did I make a mistake? No, we were right. E to the 4t, 3 plus 2t, 2 plus t. See? You could use either method. And it works. Either this much space or this much space. Whatever one you like. Okay. Good? All right. You probably don't want me to do that on every problem. But it's good to see it once. Number 6. Solve x prime equals minus 3, minus 4, 2, 1x with some initial conditions. X of 0 equals minus 1, 3. I think I know what's coming. So we'll just enjoy it for a moment. Just, the ambiance. As we start with our a minus lambda I. All right, so this is minus 3 minus lambda, 1 minus lambda, subtract 2 times negative 4. Negative 3 plus 3 lambda minus lambda plus lambda squared plus 8, which would be lambda squared plus 2 lambda plus 5. We try to factor. We do not succeed. We try harder. We still do not succeed. So what can we do? Quadratic formula, or completing the square. We'll do quadratic formula because I think more people are comfortable with that. So we throw this in. Lambda is negative b plus minus square root b squared for...
Wait a second, that's going to give us a complex.
That's okay. It's perfectly fine. It'll be complex whether or not we use the quadratic formula. All right. So, cool. 4 minus 20 is negative 16. The square root of negative 16 for I. So we end up with negative 1 plus minus 2i. Okay. So we have two options. Either one of them we can fit in the page. The other one we can fit in half a page. Let's do the one we can fit in half a page first. And then you can decide if you want to see the other one. Okay. So what's the quick way to do this? What formula? Yeah. E to the AT. So there's this nifty formula, which of course we all have memorized because it's so cool. So, but I'll just write it here just because, I like to have reference. And, okay, so e to the AT. Now this is only for cases when you have complex eigenvalues. If it's not a complex eigenvalue and you pull this formula out, what will happen? You'll lose points. We don't want to lose points. We want all the points. All right. So e to the alpha t cosine beta ti, 1 over beta, e to the alpha t sine beta t, a minus alpha I. All right. So what can we do? Well, we plug it in. Now in our case, when we talk about alpha and beta, we're talking about alpha plus minus beta I. So alpha is negative 1, beta is positive 2. So we have that we get e to the minus t cosine 2t times the identity matrix, which looks like 1, 0, 0, 1, plus a half, because 1 over beta. E to the minus t sine of 2t, a minus alpha I. So here, we're going to subtract off the diagonal, not the eigenvalue, but just the real part. So we're going to subtract negative 1. So when you subtract negative 1, it's like adding 1. So it'll become negative 2, negative 4, 2, 2. Did I do that right? Some people are skeptical. That's all right. It's okay to be skeptical. All right. With this part done, well, we'll push it a little bit more. Actually, we don't have to. All right. Now, that's our e to the at. We have initial values. What do we do once we have our e to the at? Well, I think you said plug in, but not quite plug. What do we want to do? We want to multiply by x0. So x is e to the at times x0. Once we carry out this computation, we're done. Over. Game over, man. Game over. So we have e to the minus 2t cosine 2t 1001. 1/2 e to the minus t sine of 2t. 2 minus 4, 2, 2. All this times minus 1, 3. Now, the nice thing is you can take this minus 1, 3 and you can take it into both pieces. So this is e to the minus t cosine of 2t 1001 times minus 1, 3. We'll go and figure that out in a second. 1/2 e to the minus t sine of 2t. 2 minus 4, 2, 2, minus 1, 3. Okay, if I take... Wait, oh. Aha, thank you. Thank you. I was copying that wrong. It's a copy error. Notoriously, that's where people make their mistakes. See, that's why we should do it two ways. And then when we get... Oh, no. No, you don't have to do it two ways. You just have to be careful to do it right the first time. What happens when you multiply the first two together? You get negative 1, 3. Because this is identity. It's acting like 1. Okay, this one is a little bit harder. So now that we have the right sign, 2 minus 12, also known as negative 10. Minus 2 plus 6. 4. Okay, so that says e to the minus t cosine of 2t minus 1, 3. There's a half here. Let's put that half inside. So plus e to the minus t sine of 2t negative 5, 2. And we can even put it all together. So this ends up being minus e to the minus t cosine 2t minus 5 e to the minus t sine of 2t, and 3 e to the t cosine of 2t plus 2 e to the minus t sine of 2t. Okay. That's the answer. Now the other way to do this, I don't know if I want to do it the whole way. Can I talk a few minutes about it? The other way to do this, if you didn't remember e to the at, is you say, okay, so we know our eigenvalues are negative 1 plus minus 2i. Now at this stage we say, okay, we're going to find eigenvector for just one of them, the negative 1 plus 2i. And so we do our a minus lambda I. So this would become minus 2 minus 2i, minus 4, 2, 2 minus 2i, times something equals 0, 0. And this is a time when it's really handy to remember the rule. Just say, all right, pick a row, write it backwards. The bottom row seems pretty nice. So if we write that backwards, that's 2 minus 2i, 2, and I'll flip a sign. So this is an eigenvector, but one of the nice things about eigenvectors is you can scale. I can pull out a half. So 1 minus I minus 1. So here's my eigenvector I'll use. Now at this stage, you say, okay, you're going to say, all right, I have a solution that looks like E eigenvalue T eigenvector. This is what our solution typically looks like. And our idea is to say, great, split into the two parts. So split into the real and the imaginary parts. And what will happen is because these eigenvectors and eigenvalues come in pairs, the real parts and the imaginary parts are solutions. And so you end up with the following expression you have to play with. Namely, e to the minus t cosine 2t plus I e to the minus t sine of 2t. And this part, to be clear, comes from the e lambda t. Then your eigenvector, you split it. 1 minus 1, that's the real pieces, plus I minus 1, 0. That's the imaginary pieces. So this is your V. And then, at this stage, you FOIL, you gather the real parts, you gather the imaginary parts, then you have your two solutions. Then you can get your general form for solutions, then you plug in. And then you solve for your constants, and then you put it all together, and in the end you'll get to the same place. So, in the interest of time, I already see I'm going quick. I should learn to speak at 1.25 speed. I hear that's the best way to watch my videos. Maybe 1.5. 1.5. Good to know. All right, number 7. Find e to the at. Oh, well, we've actually been doing this a lot. How hard could this one be? Okay, so first thing is you just need to know what's the right formula. So we ought to find our eigenvalues. So minus 2 minus lambda, 6, minus 2, 5 minus lambda. So, okay. Aren't you just like, oh man, I'm going to get this eigenvalue stuff down. Great. I'm ready for when I'm taking that linear algebra class at some point in the future. Going to know all the cool stuff. So, all right, but that's for the future us. So let's see, this looks like lambda squared minus 3 lambda plus 2. Huh. That factors, which is nice. Lambda minus 1 times lambda minus 2 equals 0. Huh. Disappointing. Why are we kind of disappointed now? We don't have a formula for distinct real eigenvalues. That's out of the picture. If we had repeated, we're happy. We have complex, we're happy. Distinct real, we're okay. We're not sad. I mean, it means we get to do more work. Who doesn't enjoy more work? Okay, so now that we know our eigenvalues are distinct, what's the next step? You have to do eigenvectors. Once your eigenvalues are distinct, you got to do it. You got to find those eigenvectors. So, all right, lambda equals 1. So we're subtracting 1. So that would be minus 3, 6, and minus 2, 4, times some vector gives us 0, 0. Well, can we think of a vector that does that? 2, negative 1? 2, 1. Let's see. Well, minus 6 plus 6, minus 4 plus 4. Ah, works. Good. You can always just pick a row, write it backwards, flip a sign, and then you can scale out as needed. Okay, so we have an eigenvector. All right, well that's good. Well, we have one eigenvector. Lambda equals 2. So we subtract 2 now. So we're going to have minus, got too early with my color. Minus 4, 6, minus 2, 3. Times some vector equals 0, 0. What's our vector? Or what's a vector? There's often many. 3, 2. All right. So, life's good. We have our solutions. So what we now have at this point is we say, okay, we have our x1, e to the eigenvalue t, eigenvector, and we have our x2, e eigenvalue t, eigenvector. How do we get from there to e to the at? And is there something on the formula sheet that can help us? So e to the at is phi of t, phi 0 inverse. So what is phi of t?
Isn't it both are like each eigenvector, right? The whole x1 and x2 and so on.
Yeah, so phi t, so this is our fundamental matrix. Now, fundamental matrices are not unique. There's lots of ways to get them in that there are lots of ways to express x1 and x2. But the key is to say, okay, you start with some solutions and the columns, you know, as the character from the Lord of the Rings, column, column. And you fill them, the solutions go into the columns. Okay, so this is phi of t. Good. So phi is pretty easy once you have your solutions. But that's not e to the at. We have to now do phi 0 inverse. So, all right, let's start with phi 0. When we plug in 0, what do we get? Well, 2, 3, 1, 2. So let's take phi 0 inverse. So make sure you know how to take inverses. So if I'm taking the inverse of a 2 by 2, what goes in the front? 1 over the determinant. In this case, it'd be 4 minus 3. Oh, that's nice. That's 1. Wow, what are the odds? Okay. Now, the next thing is you come to the diagonal. Now, currently, the diagonal is 2, 2. But now we're going to switch it. So instead of being 2, 2, it's now 2, 2. Exactly. You knew it. Good. Now, off the diagonal, what happens? Negative. Yeah. We change the signs. So it's negative 3, negative 1. So we get 2 minus 3 minus 1, 2. All right, so we're almost done. So it was great that we ended up with the determinant of 1. I think it was because whoever wrote this, which was me, did not want whoever did this, which was also me, to deal with fractions. So e to the at, well, I didn't write everything on the exam. I did try to get things a little bit nicer. Hopefully. I haven't taken it yet. I'm doing that tonight. Phi t, phi 0 inverse equals 2 e to the t, 3 e to the 2t, e to the t, 2 e to the 2t, times 2 minus 3 minus 1, 2. So now we're just one matrix multiplication away from being done. 4e to the t. Subtract 3e to the 2t. Minus 6 e to the t. Plus 6 e to the 2t. 2e to the t. Subtract 2e to the 2t. Minus 3e to the t. Plus 4e to the 2t. And for e to the at, we're done. Good. All right. Any questions? 2 to go. Now, the last 2 are going to get us into non-homogeneous. So, there are 2 options when you have something that's non-homogeneous. We'll go ahead and mention them now. So non-homogeneous. Whoops. I can spell non-homogeneous. So one of the hardest things about the subject is learning how to spell. Okay, so option 1 is what we call undetermined coefficients, and it runs pretty much like undetermined coefficients. So it's very familiar to us. Option 2 is variation of parameters, which runs kind of like variation of parameters in a weird way. It doesn't feel like it, but it really is when you stare at it long enough. So, what's the punchline? Undetermined coefficients, we are at least meh on. Maybe we're not excited about it, but we can do it. Variation of parameters, we usually are not very happy with. And you want to avoid it. So if possible, maybe we'll have like one of those Mona Lisa smiles where like just one of the corners is going up. And then the eyes will follow you as you move around the room. So the punchline here is, if you have an option, go with undetermined coefficients. Now, how do you know if you have an option? Well, there's no instruction, so that's good. And you check the function. You say, well, what kind of things do I see in my function here? Well, the t is what I see. I care about the pieces here. So the functions I see are t. Like, t, that's nice. I like t. So for undetermined coefficients, you need things that look like powers of t to whole numbers, exponentials, sines, cosines. If that's what you've got, life is good. Undetermined coefficients, and you're off and running. Not that, you don't have a choice.
Did you say in terms of t with whole numbers, so like t to the 1/2 would not be a good option?
T to the 1/2 would not work. No. All right. So, we're going to do undetermined coefficients on this one. So, what's the first thing when you're faced with a non-homogeneous problem? Find xc. Yes. So we want to find xc. So now that means we're solving x prime equals minus 6, 2, minus 6, 1, x. So in other words, we're dropping off that last part. That's what we mean by finding xc. And we're like, wow, this feels like the kind of thing we've been doing. Because it's the kind of thing we've been doing. And so hopefully, because we're really good at it by now, we've been doing it for an hour and a half, almost 2 hours. We're getting really good at doing this. All right, so take the determinant of a minus lambda I, and let's see, that would be minus 6 plus 6 lambda minus lambda plus lambda squared plus 12 equals lambda squared plus 5 lambda plus 6, which does factor, so that's good. That's lambda plus 2 times lambda plus 3. So our eigenvalues are -2 and -3. Now, looking ahead, this is actually some good news, because when we look here, what wouldn't we want as an eigenvalue? Anyone see what would be bad as an eigenvalue? Yeah, 0 would have been bad, but we didn't have that, so that's okay. All right. Now, if we were interested in xp, we could actually stop here, but we want the whole general form, so we really do need to find the whole xc. So eigenvalues, all right, lambda equals -2. So we're going to subtract -2, but subtracting -2 is the same as adding 2. So -4, 2, -6, 3, times something gives 0, 0. What's the something? 1, 2. 1, 2. There are other things that work, but that's probably the nicest way to write it. Lambda equals -3. All right, so in this case, subtract -3 is the same as add 3. -3, 2, -6, and 4. What's something that works here? 2, 3. Now, by the way, I didn't write the whole thing equals 0, 0. By the way, if it works for one row and doesn't work for the other row, what does that mean? Something is wrong. Either your eigenvalue is wrong, or you did a minus lambda I wrong, but something is wrong. Look for ways to check your work. The sooner you fix mistakes, the more points you get. I know, I'm making it sound like this is all a game, and we're trying to maximize our score. But that's because this is kind of like a game. We're trying to maximize our scores. So that's why I keep harping on that. So, now we're ready to start talking about our XP. Now the way I like to think about undetermined coefficients is I'm making a list. I look at the piece, it's not a homogeneous piece, and I say what functions are involved. Well, what functions do we see? Don't worry about the coefficients. We see t. That's the only function. Now we start checking. Do we have any powers of t? Yeah, we do. If we have powers of t, what else do we need to include? Lower powers of t. So what else needs to be added to our list? 1. T to the 0 power. All right. Do we have any sines or cosines? Nope. That's good news for us. Do we have any overlap? So here, we didn't write it down, but our xc is some constant e to the minus 2t 1, 2 plus some constant e to the minus 3t 2, 3. So when we talk about the overlap, we're talking about these functions e to the minus 2t and e to the minus 3t, which is in some sense why we said once we knew negative 2 and negative 3, we had a pretty good idea of what was going on. So any overlap? No. We're good. So that's great. Now we've made our list. We can stop and check it twice. Yep, good. All right. So we now can say XP looks like, go through your functions on your list, t times some unknown vector, AB, plus 1 times some unknown vector, CD. Or if you like, we can smoosh it together, A times t plus C, B times t plus D. Now, is this XP? Well, once we figure out the right choices for A, B, C, D, yes. But until we have A, B, C, D, we don't actually have it. So how do we get A, B, C, D? What? Plug it in. Yes. Plug it in. Plug it in. Okay, so we plug it into the whole thing. So let's start with the left-hand side. Take the derivative. What do you get? AB equals minus 6, 2, minus 6, 1, AT plus C, BT plus D, plus 6t minus 3t. Now, a lot of this is just going through and carrying out the computations. So we have minus 6, A times t plus C, plus 2, B times t plus D. So I'm just matrix multiplying. And we'll even throw in the 6t on the end. Then we have minus 6, A times t plus C, plus 1, B times t plus D, and then minus 3t. And that equals A times B. Or, sorry, the vector AB. Good. Well, we can clean this up a little bit more. Let's group our t's. We have minus 6a plus 2b plus 6. Our constants, and now I wish I had bigger paper, minus 6c plus 2d. Downstairs, minus 6a plus b minus 3, that's our coefficient of t, and then minus 6c plus d, that's our constant. All right. Well, so we have function on the left, or if you like, matrix on the left equals matrix on the right. I should have said vector, but a vector is just a matrix that's gone on a diet. So the top has to match. Bottom has to match. These are both polynomials. So it tells us that the coefficients have to match. Here I have a coefficient for t, minus 6a plus 2b plus 6. What does that match on the left-hand side? It matches 0. Because there's no coefficient for t on the left-hand side. So no coefficient means 0t. Here I have minus 6 plus 2d. I know it's not very legible. That's the constant on the right-hand side. It has to match the constant on the left-hand side, which is a, because that's a constant. Similar for the other entry. Minus 6a plus b minus 3 has to equal 0, because there's no coefficient for t. Minus 6c plus d has to equal b.
4 equations, 4 unknowns. Let's do it.
Sorry, what?
4 equations, 4 unknowns.
Yeah, 4 equations, 4 unknowns. Wow, life is good. Okay, so how can we make progress? So people have said 4 equations, 4 unknowns, but look here. What do you notice about that? It's 2 equations, 2 unknowns. So if you work first with your coefficients for t, then work for your constants, you'll see that the coefficients for t will be something you can actually solve. And then you can feed that into solving the others. Okay, so let's clean this up a little bit. We don't need to do too much here. We could say minus 6a plus 2b equals minus 6. Minus 6a plus b equals 3. What can we do to these 2 equations to get some cancellation?
Why is it minus 6a?
Why is what?
Never mind.
Okay. It's already gone out of my mind. Subtract. 6a's cancel. 2b minus b is b. Minus 6, subtract 3, minus 9. All right, progress. B is minus 9. Well, we can plug that in to either equation. Minus 6a minus 9 equals 3. Moving things around, we get that 6a is negative 12. So a is negative 2. Okay, now we've got 2 constants. All right, so updating. Negative 6c plus 2d equals negative 2. That's a. Negative 6c plus d is equal to negative 9. That's b. What can we do here? Yeah, we can subtract again. Wow, that's cool. It's almost like problems work. Okay, the 6c's cancel. 2d minus d is d. Negative 2 minus 9, 7. So now we know what d is. D is 7. Minus 6c plus 7 equals minus 9. Okay, we can move the 9 across, move the 6c across. That would tell us that 6c is equal to 16. Yes? So what is c?
8/3.
8/3. That's okay. Fractions aren't too bad. We can have fractions. All right, so updating. We found A, B, C, D. So that tells us our XP. So we just have to make sure we find everything in the right place. So minus 2t, because there's the A, plus 8/3, the C. Then downstairs minus 9t, that's our B. And then plus 7. Okay, so there's our XP. Are we done? What's left? General form. So what is the general form? I mean, we found XV and we found XP. What?
Combine them.
Yes. Their powers combined, they are the answer. So the general form is both of them together. So, in this small sliver of paper left, we can say our solution is we copy our xc. And it doesn't matter which one you put first, xc or xp. You just make sure you get both of them. And then you add in your xp. And you're done. All right. Question, I see?
You had mentioned earlier about our eigenvalues. If we're given 0, would it be really bad? What do you mean by that?
Well, we would have had overlap. And overlap would mean more things on our list. But right now, we have 4 unknowns. More overlap would have been 6 unknowns. Or 8. Oh my. That's a lot. Are there any other questions? All right, well that brings us to number 9. Our final one for tonight. Using variation of parameters, find xp. So the good news is we don't have to find the general form, we just have to find one little tiny piece. For x prime equals 3, 1, minus 4, minus 1x, plus 4 e to the t, 2 e to the t. Now, could we use undetermined coefficients? Yes. But we're not supposed to. We wouldn't get full credit. This, I think, is actually a rare case. It's very rare where undetermined coefficients is less efficient than variation of parameters. We'll see why momentarily. I say that because this isn't just random numbers. Okay, what's the first thing we need to do? Well, if we're doing variation parameters, it's probably helpful to remember the formula. So we'll write that down. E to the at integral e to the minus at f of t dt. So, what do we need to find? We got to find a lot of these things. E to the at, e to the minus at. Okay, and then we got to work through our layers. An onion problem, right? Because there's layers. You got to keep chipping away, one computation at a time. And as with onions, there will be some tears perhaps. But to get to e to the at, we have to know what kind of matrix we're dealing with, which means we've got to do eigenvalues. So it's just, you just know, it's just like I'm doing eigenvalues a lot. Be ready. Get your eigenvalue game and hone it so that you'll be like, yeah, no doubts. I'm going to get every single eigenvalue right. Because that's probably going to give me like 10 points on this exam. All right, so let's see. We get minus 3 lambda, plus lambda squared, plus 4, which is lambda squared minus 2 lambda plus 1. That's lambda minus 1 squared. Ooh. Repeated eigenvalues. That's good news. Now, if we were doing undetermined coefficients, what would our feeling be right at this moment? Correct. That is the correct feeling to have. Why? Overlap. Lots and lots of overlap. And so we would have to do not just e to the t, we'd have to do e to the t, t e to the t, t squared e to the t. 6 unknowns. Not looking forward to that. But that's okay, we're not doing it. That's not even an option. All right, so what's the first thing, not the first thing, we already said the first thing are the eigenvalues. What's our next thing to find? E to the at. Do we have a nice way to find e to the at? Yes, because the formula sheet still exists. So e to the t, this is our I plus a minus lambda I. Okay, in our case, remember that lambda is 1, so we're subtracting 1. So that's 2, 1, minus 4, minus 2. T. So that's e to the t, 1 plus 2t, t minus 4t, 1 minus 2t. That's e to the at. What else should we find while we're at it? We need also e to the minus at. Now, we don't have to start from scratch. In fact, that's the worst thing to do. What's the best thing to do? Well, this is e to a positive t. We can think of this as e a negative t. So we can say everywhere you see a t, put negative t. So t's become negative t's. E to the minus t times 1 minus 2t minus t, 4t, 1 plus 2t. All right. So we have our pieces in play. Now we just start working through our layers. The first layer, e to the minus at times f of t. Our f of t is the non-homogeneous part. So we have e to the minus at f of t. Well, that's e to the minus t, 1 minus 2t, 4t, minus t, 1 plus 2t. Now, f of t, I can pull out an e to the t, and then it's 4, 2. Is there anything we can do, or that we see that like, ooh, that's nice? Yeah, see how we have e to the negative t and e to the t? It's almost like whoever wrote this problem wanted something nice to happen, because they were going to have to do this problem. Unlike the exam, we don't have to do the exam problems. No, we love you guys. Come on. Of course they're going to be nice problems. We're always taking care of our students. That's why we have, a 2.7 rating on Rate My Professor. Something. All right. 4 times 1 minus 2t plus 2 times minus t. 4 times 4t plus 2 times 1 plus 2t. Yes, I'm just do. Well, that would be 4 minus 8t minus 2t is minus 10t. Then downstairs we'll have a 2, because it's 2 times 1. Then we have 16t plus 4t makes 20t. Okay? That's the first layer. One layer down. What's the next layer going to do? The integral. So now we have to integrate e to the minus at f of t dt. We'll say, well, we know what that is. That's the integral 4 minus 10t, 2 plus 20t dt. Well, whoops. We can just integrate. What's the integral of 4 minus 10t? 4t minus 5t squared. Integral of 2 plus 20t. 2t plus 10t squared. Okay. Wow. We're actually making good progress. Cool. Now, the next thing for us to do, our last layer of our onion, e to the at times what we just found. Okay, so we copy our e to the at. We have e to the t, 1 plus 2t, t minus 4t, 1 minus 2t. Well, we're going to have a little bit of work here, but that's okay. We'll work it out. That leaves us an e to the t in front, 1 plus 2t times 4t minus 5t squared plus t times 2t plus 10t squared minus 4t times 4t minus 5t squared plus 1 minus 2t times 2t plus 10t squared. In for a penny, in for a pound. We're going to go all the way. So, equals e to the t. Distribute 1 times 4t, that's 4t minus 5t squared plus 8t squared minus 10t cubed plus 2t squared plus 10t cubed. Downstairs, minus 4t times 4t minus 16t squared plus 20t cubed plus 2t plus 10t squared minus 4t squared minus 20t cubed. Does anything nice happen? No? The t cubes all cancel. So we are left with our answer, which is upstairs we have, let's see, 8t squared, 2t squared, that's 10t squared, minus 5t squared is 5t squared plus 4t. Downstairs, we have a minus 16t squared, a minus 4t squared, that's minus 20 plus 10 makes minus 10t squared plus 2t. And we're done. That's our answer. Now, you might wonder, I fed this into Wolfram Alpha, and it doesn't match. Well, two things. One, I may have made a mistake, but I don't think so, because you've been checking me. Thank you. I appreciate that. But the other thing is, XP is not unique. You can add anything into XC, and it's still a valid XP. And so, just because you don't always get what Wolfram Alpha gets, it doesn't mean you were wrong. Anyways, thank you for being so patient. I know it's been a while here. Good luck.